All right, let's get into it. Today, we're putting on our lab coats and becoming chemical detectives. Our mission, if you choose to accept it, is to tackle one of the most fundamental questions in all of chemistry. A question that's key to everything from how strong your medicine is to whether your food is safe. And that question is, how much is actually in there?
I mean, think about it. How strong is the vinegar in your kitchen cabinet? Seems like a pretty simple question for us today, right? But, for chemists a couple of hundred years ago, this was a huge puzzle. Answering it took some serious cleverness, and that's exactly where our detective story kicks off.
So their method was surprisingly hands-on. What they do is take a vinegar sample and just start adding this stuff, potassium carbonate, while watching it like a hawk. All that fizzing and bubbling, that's carbon dioxide gas, and it's being released because the powder is reacting with the acetic acid, the very thing that gives vinegar its kick. The moment the bubbling stopped, they knew the reaction was over. The more powder they had to use to stop the fizz, the stronger the vinegar. It was simple, it was visual, and honestly, it worked remarkably well. That simple little experiment was actually the start of an entire field of chemistry. So here's our game plan for today. We're going to start with that old question, then we'll open up the modern chemical detectives toolkit. We'll get into two key techniques, one called titration and another that's all about weighing. And finally, we'll connect all the dots and see why this kind of chemical math is so important in our world today. So that whole journey, from a basic test in a kitchen to a super precise modern lab, that's really the story of a field we now call quantitative analysis. It's just the fancy, formal name for the science of figuring out how much. And this right here is the heart of it all. See, it's one thing to know what is in a sample, but quantitative analysis is all about asking how much is in there. Think about it like this. It's the difference between a detective knowing there's poison in a drink and knowing if it's actually a fatal dose. It's all about precision. It is, quite literally, chemical detective work.
Now, every good detective has a trusted toolkit, right? Well, the chemical detective is no different. We're going to look at two master techniques they use to crack these cases. And what's so cool is that they come at the problem from completely different angles.
And here they are, the two core philosophies side by side. On the left, we've got titration, which is all about solving the mystery through a carefully controlled reaction. On the right is gravimetric analysis, which is all about separating what you're looking for from everything else so you can just, weigh it. So the choice is, do you solve the case by reacting or by separating? Let's dive into the first tool on our kit, titration. This is a truly classic, kind of elegant technique, and it's built on a really simple idea. You use a substance you know everything about to uncover the secrets of one you don't. Okay, let's get the official lingo down. The titrant, that's your known solution. You add it with extreme precision from that long glass tube you see in labs, called a burette. And the analyte, that's your mystery substance, waiting down in the flask. The whole point is to add that titrant drop by drop, waiting for that perfect moment when the chemical reaction is totally complete. But how do you know when to stop? This is the aha moment. The perfect theoretical point where the reaction is 100% done is called the equivalence point. But, we can't see individual atoms, so we use a clever little trick. We add a special dye, an indicator, that just, bam, changes color at the exact right moment. That visible color change is our signal, the end point, and it tells us the case is solved. And the math behind it follows this really clean three-step logic. First, you hit the brakes when the color changes, and you measure exactly how much of your known solution you used. Step 2, you use what's called stoichiometry, which is just the chemical recipe for the reaction, to figure out how many molecules of your unknown were in the mix. And finally, you use that number to calculate its original concentration. It's that simple. Measure, convert, and calculate. Okay, but what if a nice, clean reaction with a pretty color change just isn't in the cards? Well, time for our second tool. What if, instead of reacting it, you could just pull the evidence right out of the sample and put it on a scale? That's the whole idea behind gravimetric analysis. So with this strategy, the goal is to force your target substance, the analyte, to change its physical state so it's super easy to separate. The most common way to do this is to add another chemical that makes the dissolved analyte clump together and literally crash out of the solution as a solid. And that new solid that forms, that's called a precipitate. As you can probably guess, it's a very physical process. You make the solid precipitate, then you isolate it by pouring the whole messy mixture through a filter. Then you have to carefully dry it because you don't want to be weighing any water, and then you place it on a super precise scale. That final mass is the critical clue that lets you work backward and calculate exactly how much of your analyte was in the original sample. Now, let's look at our really specialized gadget in this part of the toolkit. It's perfect for when the mystery isn't just how much, but what is the stuff. It's called combustion analysis, and its whole job is to find a compound's deepest secret, its empirical formula, which, by the way, is just the simplest ratio of atoms in the molecule, kind of like its basic recipe. Now, it sounds destructive, and yeah, it is, but it's also incredibly precise. You take a tiny pre-weighed sample and you just burn it completely. If your sample is a simple hydrocarbon, for example, all its carbon atoms will turn into CO2, and all its hydrogen atoms will turn into water. Special chambers in the machine capture these gases and weigh them. From the final weight of the CO2 and the water, you can actually work backward to find the exact mass and the ratio of carbon and hydrogen in your original mystery sample. So let's say you burn a tiny piece of polyethylene, the plastic in a Ziploc bag, and you run all the numbers. What you get is its fundamental building block, CH2. 1 carbon atom for every 2 hydrogen atoms. You've just cracked the code and found its empirical formula. So there we have it, 2 powerful detective techniques. One is all about reacting, the other is all about separating. But why are these methods, with roots that go back centuries, still so incredibly important in our world today? Well, the answer is pretty simple. Precision matters. It matters everywhere. From making life-saving drugs to making sure our environment is safe, we have to know exactly how much of something is present. Is there enough of the active ingredient in that pill? Are the levels of that pollutant in our drinking water below the legal safe limit? These techniques, in all their modern high-tech forms, give us the definitive answers. They are the absolute foundation of quality control and safety. So in the end, it all comes back to that one simple, powerful question. How much? From the caffeine in your morning coffee to the salt in the ocean, quantitative analysis is the invisible detective work that measures and manages our world. It keeps us safe and it keeps our science honest. So next time you look around, maybe ask yourself, what critical quantities are hiding in plain sight, just waiting for a chemical detective to come along and measure them?